In this second segment of this tutorial, we will be demonstrating how the orbitals of the atom of phosphorus get sp3d hybridized in the formation of phosphorus pentahydride. We will now demonstrate how the atomic orbitals of the phosphorus atom get hybridized to produce 5 sp3d hybrid orbitals. As depicted by this model here, you can see that the 3s orbital of phosphorus is having 2 electrons, and each of its 3p orbitals is having a single electron each. But phosphorus needs to bond with 5 hydrogen atoms, each with its electron. But we can see that there are only 3 electrons available for bonding here. So the theory is that, again, one of the electrons from the s orbital gets promoted into one of the vacant 3d orbitals. And everything gets hybridized. This s orbital gets hybridized. These 3p orbitals get hybridized along with a single d orbital to form 5 sp3d hybrid orbitals. So these are 5 sp3d orbitals, meaning you're having an s orbital with 3 p orbitals and 1 d orbitals. So you have a total of 5 identical orbitals. And the next job is for us to put this around the central phosphorus atom to show how they bond with these 5 hydrogen atoms. The empirical evidence suggests that 3 of these sp3d hybrid orbitals will form a trigonal planar arrangement around the central phosphorus atom with a bond angle of 120 degrees here. And these 2 other ones are at right angles to those. So bonding these with hydrogen now will get the following structure. We will have a trigonal bipyramidal arrangement of the bonds, and the geometry of this molecule we call a trigonal bipyramid. So this molecule we call an AX5 type of molecule. If you have AX4E type of molecule, the rule is that you remove that bond there and lone pairs are put at the side here. In such a case, this molecule will have a seesaw shape. You have to remove another one. Lone pair is placed here. So the rule is that you keep removing from the radial atoms until you end up with a linear molecule, okay? In every case, you're going to have sp3d type hybridization, but the geometry will change until you end up with a linear arrangement like this, where you can go forward. Okay. In this third segment, we'll be demonstrating how a pi bond is formed between the 2 carbon atoms in the ethene molecule, as these atoms undergo sp2 hybridization of the atomic orbitals. So these represent the outer orbitals of one of the carbons in the ethene molecule. And this is the 2s orbital with its 2 electrons. And you're having 3 2p orbitals, with 2 of them having 1 electron each, and this one here is a vacant one. The same thing is happening on this left side here, that represents the orbitals of the other carbon atom, and here's your 2s orbital with 2 electrons. And again, you have 3 of these 2p orbitals, with 2 of them having 1 electron each, and this one is vacant. So this is the theory. Again, the theory is one of these electrons here from this s orbital gets promoted into that vacant p orbital here, and the same thing happens here. Something similar to that happened in the formation of methane molecule. However, there's a difference. Only 2 of these p orbitals here, along with this 2s orbital, get hybridized in this carbon atom here. And the same thing happens in this one here. These 2 p orbitals here, along with that s orbital, get hybridized. This one will remain unhybridized. That one there too. So this is what we will end up with. we will end up with 3 sp2 hybrid orbitals, and this one p will remain unhybridized. I can borrow these electrons to fill these in. Doing the same thing across the side, we end up with 3 of these sp2 hybrid orbitals, and this one 2p unhybridized orbital. Borrow these now. They are called sp2 hybrid orbitals and not sp3 hybrid orbitals because we are taking this s orbital here and we are taking 2 of these p orbitals. Same thing, this s orbital here and these 2 p orbitals here. So we end up with 3 sp2. The next job is for us to put these 4 orbitals around one carbon atom and put these other 4 orbitals around another carbon atom. And then we'll see how they bond. In placing these orbitals around the carbon atom, because they represent negative clouds of electrons, they will push each other as far away as possible to minimize their mutual electrostatic force of repulsion between them. So the next thing is for us to see how they are arranged around the central carbon atom. Putting these 3 sp2 hybrid orbitals around this carbon atom, the obvious arrangement will be that each of these orbitals will be away at 120 degrees apart. That's because they want to minimize the mutual force of repulsion between them. And they will make what is called a trigonal planar arrangement. However, the unhybridized p orbital will be aligned perpendicular to these 3 sp2 hybrid orbitals. One lobe will be at the top and the other lobe will be below. We are just putting in these electrons for the sake of convenience, right? According to the wave mechanical model, the entire lobe here is where there's a probability of finding electrons. The same thing will happen to this other carbon here. The next thing what is going to happen is that these 2 sp2 hybrid orbitals will overlap to form a sigma bond. So that's the next thing we'll show you. So a sigma bond is formed between the 2 adjacent sp2 hybrid orbitals. The next thing that's going to happen is that hydrogen atoms will form sigma bonds with the 4 other sp2 hybrid orbitals, 2 on this carbon here and 2 on this other carbon here. So you can see now how those 4 hydrogen atoms have bonded with those 4 sp2 hybrid orbitals, and you have in the middle here the sigma bond that we've spoken about just now. Now we have to talk about these unhybridized p orbitals. Now what is going to happen is this. Because these electrons here are not localized, there is what is called sideways overlap of the atomic orbitals. If we can use these 2 Orlin-Meyer flasks to rest this model on, we can now show what will happen with these 2 unhybridized orbitals. There will be what is called sideways overlap of the electron cloud at the top here and below there. We'll use this structure here to represent a lobe of the negative cloud is formed above this sigma bond here, and another one to represent the lobe that is formed beneath the sigma bond. So our final structure can be represented by this model here. These are the 2 carbon atoms here. On each side you have one sp2 hybrid orbital here, another one here, and one that was in the middle here that form a sigma bond with that one from across the side. This one here forms a sigma bond with hydrogen atom. This other one here forms a sigma bond with this other hydrogen atom. And these 2 unhybridized p orbitals form what is called this pi bond. There was sideways overlap of the electron cloud from that lobe there and this other lobe here. And this is the model that represent ethene. So a pi bond is formed by sideways overlap of two unhybridized p orbitals. If you have two sets of unhybridized p orbitals, then you're going to have two pi bonds. In such a case, there will be sp hybridization of the atomic orbitals of both carbon atoms. And we don't have time to do that now. I can quickly share what would have happened, right? If you want to bear with me. If we had a acetylene molecule, there would have been what is called sp hybridization of the atomic orbitals. You would only have had an s and a p orbital getting hybridized. So you only form two sigma bonds. One will form a sigma bond with this hydrogen here. This other one will form a sigma bond with the hydrogen. And the ones between there is going to be forming a sigma bond there. These two other unhybridized p orbitals would then form another lobe here and another lobe here. And that would have given you two pi bonds. Okay? And this is how the acetylene molecule would have looked like. One lobe at the top here, another one here, and then there would have been one sideways here and one sideways there. And that is how acetylene would have worked, and that would have represented sp hybridization of the carbon atoms.